Auzubillahi minash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum class and welcome back. Today is the third lecture of the course of partial differential equations. In this lecture we will solve the heat conduction problem where with separation of variable. Separation of variable is often the most simplest method for the solving solution of the heat conduction equation. Consider the problem. Consider consider the heat conduction equation. As we have derived it in our previous lecture, a typical heat conduction equation can be written in terms of partial differential equation as ut is equal to alpha square u double x. And together with this PDE, we have a set of boundary conditions u at 0t is equal to 0, u at n t is equal to 0. Assume that both the end of the rod are fixed at 0 degrees centigrade. We will fix the ends at 0 temperature. Later on we will extend our investigation for non-zero temperatures. Assume the initial temperature of the rod is given by some given function f of x. Suppose this data is given to us. So, what will be the solution of this problem? The solution of this problem means a function of two variables x and t which satisfy this PDE as well as this function satisfy this condition and this condition, and also the same solution satisfy the initial condition. So our objective is to find a function, an analytical function u of xt which satisfy all these four conditions. You have the PDE, the temperature at the left end, temperature at the right end, and the initial temperature of the rod. So before going to solve this problem, we will recall some important result from the ordinary differential equation. The first problem is the equation of the form y prime plus lambda t is equal to 0. This is a first order differential equation. You can solve this problem with a variety of methods. I will apply the method, the auxiliary function. The auxiliary function of this equation is m plus lambda is equal to 0, which gives us the result m is equal to minus lambda. So this is the root of the auxiliary equation. So in terms so as the root of the equation is negative, so the solution of this problem will be some constant c multiplied by e power minus lambda t. This is the first result. If you substitute this equation into this ODE, this equation will satisfy this ordinary differential equation. Now note that this is not one solution. This is one parametric family of solution. Means y of t is equal to 2 e power minus lambda t is this also a solution of this problem. Y of t is equal to 3.5 e power minus lambda t is also a solution of this problem. Okay, So this is basically one parametric family of solutions. Now consider the second order differential equation, x double prime plus lambda x is equal to 0. This is second order differential equation. The auxiliary equation of this ODE is m square plus lambda is equal to 0, which gives us m is equal to plus minus iota lambda. Now the root of the auxiliary equation is imaginary. The real part of these roots are 0, so the solution of this problem can be written as x of t is equal to c1 cos lambda t plus c2 sin lambda t. Now this function satisfies this ordinary differential equation. Now note here that this is two parametric family of solution, one parameter c1 and one parameter c2. So this is also an infinite, uh, this also represents infinite set of solutions. Okay. Now let's move to our main problem. Our problem is to find the solution of this heat conduction phenomena. So assume that if the solution of the problem exists and is unique, then assume that it have a shape u of xt is equal to x multiplied by t of t. This is our first assumption. This assumption means that if there is a solution of the problem, then that solution may be in the form of product of two functions of different variable, one function of x multiplied by function of t. So this is a basic assumption. After this assumption, you will see that how beautifully this assumption converts this problem into much simpler problems. So if the solution of this problem exists in this shape, then this solution must satisfy this PDE. Okay, so we will substitute this PDE into this assumption, this solution into this PDE. What we get? We get x at x t dash at t. This is basically u t. u x u double x is equal to x double x t at t. Substituting these estimates into this problem, we get x t dash at t is equal to x double dash at x t at t. Which can be simplified in this form. You can divide this expression by the term t of t, you will get this thing, and when you divide this expression by x of x, so you will get this thing. Now look at this expression. This expression tells us that two quantities are same. One quantity depends on x and the other quantity depends on t. And this equation says that these two quantities are same. So logically this is not possible. A function of x may not be equal to a function of t. So the only possibility is if these things are constant. If these things are constant, then it is possible that a function of x is equal to a function of t. I will give you a short example. 1 is a function of x, 1 multiplied by x power 0. 1 is also a function of t. Now both of these things are same. So a function of x and a function of t is 0 is same only in that condition when both of these are constant. So we will assume that these quantities are constants. X double dash x divided by x of x is equal to t dash of t divided by t of. We will assume that these things are constant and is equivalent to minus lambda square. Why we use this minus lambda square? Especially what is the role of this negative sign? It will be clear in the next steps. So this setup equation basically gives us two differential equations: x at x divided by minus lambda square and t dash at t divided by t of t is equal to minus lambda square. Okay. Again, further simplification gives us x dash at x plus lambda square x at x is equal to 0. We will call this equation A, and t dash at t plus lambda square t at t is equal to 0. We will call this equation as equation B. Okay. Now the the terms involved in the solution of the PDE must satisfy these two conditions. X of x satisfy this differential equation and t of t satisfy this differential equation. This is first order differential equation and this is second order differential equation. We will apply this method. We will apply this method to solve the first order equation and this method to solve the second order equation. Now this solution must also satisfy these boundary condition. If we substitute x by 0 in this expression, then this quantity must be 0. And if we satisfy x is equal to L in this equation, this must also be 0. So u of 0t, which is the temperature at left end, and we have fixed it at 0. This thing implies that x at 0 into t at t is equal to 0. Okay. The second condition, u at L t is equal to 0. This implies x at L t at t is equal to 0. Now these two equations gives us information about the solution of the problem A. We cannot say that t of t is 0, because if we say that the t of t this function is 0, then we end in a trivial solution. So we will say that this thing must not be 0. And so what we get? We get x at 0 is equal to 0, x at L is equal to 0. So the 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 function of x in the solution satisfy this ordinary differential equation, and if this function satisfy these two conditions also, then the resultant solution will satisfy these boundary conditions. Okay. Now let's solve the first order equation. T dash of t plus lambda square t of t is equal to 0. The auxiliary equation is m plus lambda square is equal to 0, which gives m is equal to minus lambda square. So the solution t of t is equal to c1 e power minus lambda square to alpha square t. We are missing some things. If we substitute these quantities into the main equation, we will get alpha square. So here make these necessary corrections. Okay. So this is the one parametric family of solution of the first order ordinary differential equation. The second order equation is x double dash at x plus lambda square x at x is equal to 0. The auxiliary equation related to this problem is m square plus lambda square is equal to 0, which gives us m is equal to plus minus iota to lambda. Okay, so the real part of the root of the auxiliary equation is 0 and the imaginary part is minus is plus minus iota lambda. Then we can write the solution x at x is equal to c2 cos lambda x plus c3 sin of lambda x. This is the solution to this problem. Now this is two parametric family of solution. We will select those values of c2 and c3 for which these two quantities are satisfied. In short, this equation must also satisfy these boundary conditions. So in order to impose the first condition x at 0 is equal to 0, this thing implies that 0 is equal to c2 cos lambda into 0 plus c3 sin lambda into 0. Okay, so this thing means c2 is equal to 0. If we set c2 is equal to 0, then this equation satisfy the first condition, the first boundary condition. In order to satisfy so if c2 is equal to 0, then the solution become x at x is equal to c3 sin of lambda x. Now this equation must also satisfy the second boundary condition, which is x at l is equal to 0. So we will write x at l is equal to 0. This implies substituting l in this expression, we get 0 is equal to c3 sin lambda l. As in the previous step, here we cannot assume that c3 is 0, because if c3 is also 0, then the final solution x at x must be 0, which means that we will end in a, if x at x is 0, then we will end in a trivial solution. So we will select the lambda in such a way that this equation is 0. So what we get, sin of lambda l is equal to 0. Now what are the choices for the lambda such that sin lambda L is equal to 0? There are many choices. If lambda L is equal to pi, then sin of pi is equal to 0. If lambda L is equal to 2 pi, then sin of 2 pi is also 0. In short, we can write as lambda L is equal to n pi, which gives us lambda is equal to n pi over L. Okay, so basically we have infinite choices for the selection of the lambda. We will write the solution as x n of x is equal to c3 sin n pi x divided by L. Okay, we have infinite solution for n is equal to 1. This is also a solution to this problem. And this solution will satisfy both the boundary conditions also. For n is equal to 2, this is also a solution. So this means that for this problem we have an infinite set of solution. Okay, x1, x2, x3, x4, x5. Now as we have solved the we have found a function which satisfy this ordinary differential equation, and we have also solved the second order problem. So we have two solution. We have a function of t, we have get this function, and we have also calculated this function. T of t is equal to c1 e power minus lambda square alpha square t, and x at n, xn of x is equal to c3 sin n pi x over n. So from these two quantities we will construct this solution. We will write un of xt is equal to an e power minus alpha square n pi over n whole square t, n2 sin n pi x over n. Now it may be clear to you that why have we written yn instead of y, because for n is equal to 1 we have one solution, n is equal to 2 we have two solutions, another solution. In fact, for that problem, for this problem we have one parametric family of infinite solutions. Here this an is actually the combination of these two constants, c3 multiplied by c1. We will write it as an. Now recall the superposition principle for ordinary differential equations. The superposition principle of ordinary differential equation says that if u1 and u2 are two solutions to a specific problem, then u1 plus u2 is also solution to that problem. This is the superposition principle, and it is in this principle holds the linear in the linear differential equation. So this principle is also applicable on partial differential equations. Means if for a given partial differential equation we have two different solutions u1 and u2, then the sum of these solution is also the solution to the PDE. So we have infinite solution. It means that the function u of xt is equal to summation n is equal to 1 up to infinity a n e power minus alpha square n pi over l whole square t into sine n pi x over l. That means this is also solution to this problem. Okay, here we have applied the superposition principle. We have make a summation of all these solutions. Now what is the specification? What are the properties of this solution? This solution satisfies this ordinary differential equation. This partial differential equation. This solution also satisfies the first boundary condition, and this solution also satisfies the right end temperature condition. In the current state, there is only one unknown quantity a n. We will select this quantity a n such that this solution also satisfies the given initial condition. So we will substitute the initial condition is u at x0 is equal to f of x. Note that this is a given quantity. So substituting t is equal to 0 and this solution, we get u at x0 is equal to summation n is equal to 1 up to infinity. This term becomes 1 and a n sine n pi x over l, which means f of x is equal to summation is equal to 1 up to n a n sine n pi x over n. We will select these constant in such a way that the given function is equivalent to this summation. Let's write this equation into the expanded form of x is equal to a1 sine pi x over l plus a2 sine 2 pi x over l plus a3 sine 3 pi x over l. Okay, so how will we select the constant a1, a2 and a3? In order to determine these constants, we will use some properties of the sine pi lambda, sine n pi x. You may have know about this identity 0 to L sine n pi x over L multiplied by sine m pi x over L dx. What is the answer of this integration? This is a conditional answer. If m and n are same, then this integral is equivalent to L divided by 2. And if m and n are not same, then this is condition integral is equivalent to 0. This is also called the orthogonality condition of the orthogonality condition. If you are going toward the approximation theory, so in the approximation theory, this condition is called the orthogonality condition. Okay. So this property can be easily applied to construct these constant a1, a2, a3. First, we will try to calculate the a1. So what will be the procedure? We will multiply this equation by sine pi x over l, the left hand side and the right hand side also, and then when we integrate from 0 to l all the expressions. So multiplying by sine pi x over l and integrating from 0 to l dx, what we get 0 to l of x sine pi x over l dx is equal to a1 sine pi x over L multiplied by sine pi x over L plus a2 sine 2 pi x over L into sine pi x over L, and we will integrate all these terms also. We have multiplied this equation by sine pi x over L and integrate it from 0 to L, so we get this expression. Now you may see that in this integral the value of n is 1 and the value of m is also 1, so this is equivalent to L divided by 2. Now what about this one? In this integral the value of n is 2 and the value of m is 1, so this integral must be 0. The next integral must also be 0, so we get a1 into L divided by 2 is equal to integral from 0 to L fx sine pi x over L dx, or a1 is equal to 2 over L 0 to L f of x sine pi x over L dx. Okay. So the value of a1 must be calculated using this expression. Okay, this is the initial condition, this is the given function. In a problem you will be given with this condition. So if you are asked to calculate the solution, so in the solution the a1 must be calculated by this relation. So analogously the second constant must be 2 divided by L integral from 0 to L fx sine 2 pi x over L dx. Think about it. How does this expression comes? Generally we can write an is equal to 2 divided by L 0 to L 0 to L f of x sine n pi x over L dx. We will calculate the constant an by this expression. So if the constants an are calculated by this expression and these constants are substituted into this solution, then this solution must satisfy the ordinary differential equation, both the boundary conditions and the initial conditions. We will write the solution of the problem as u of xt is equal to summation n is equal to 1 up to infinity an e power minus alpha n pi over L whole square t into sine n pi x over L, with the condition that the constant an must be calculated by the integral 2 divided by L 2 divided by L. So this is the solution of the problem. This is the solution of this problem. This solution satisfy this PDE, this boundary condition, also this boundary condition, and this initial condition. Okay. In practical, if we are given a problem and we are asked to solve it, then we cannot calculate the infinite constants. Okay, this is infinite sum. So we can approximate this constant. We can use a truncated for example, if you are asked that calculate the first three term of the solution, then we will calculate a1, a2, a3, and the solution will be u of x is equal to a1 multiplied by this term plus a2 multiplied by the second corresponding term and a plus e3. Okay, so we will calculate some initial terms of this solution. It is impossible to calculate the whole infinite sum. We will solve a short and simple problem. A rod have a length of 10 meter. The specific heat of the rod is 0.5. The thermal conductivity is K is equal to 6. The density of the rod rho is 4. Both the ends are fixed at 0 degree centigrade, and assume the initial temperature of the rod is given by f of x is equal to x into 10 minus x. Design the PDE of the experiment. The first objective is to design the PDE of the experiment. The second is construct the first 5 terms of solution. Means approximate the solution up to first 5 terms. The third one is find the temperature. The third one is find the temperature at mid of the rod at time t is equal to 0, at time t is equal to 3, time t is equal to 5. So we will first design the PDE of this problem. We will construct the first 5 terms of the solution, and using that solution we will calculate the temperature at midpoint of the rod at time t is equal to 0, then at time t is equal to 3, and that at time t is equal to 5. So let's start our calculation. The PDE is, for the construction of the PDE, we will first construct this alpha square. So we know C is equal to 0.5, k is equal to 6, rho is equal to 4. Alpha square is equal to k divided by 0. Recall from the previous lecture. So this is actually 6 divided by this rho is 3. 6 divided by 2 is equal to 3. The value of the alpha square is 3. So we have calculated this parameter, so we can write this PD ut is equal to 3 into u double x. This is the PDE. Now both the ends of the rod are fixed at 0 degrees centigrade, which means u at 0t is equal to 0 and u at lt is equal to 0. Okay. Now the initial temperature of the rod is f of x is equal to x into 10 minus x. So we will write u at x0 is equal to x into 10 minus x. We have calculated the solution of this problem by we found that the solution is this one. So even the first pipe term of the solution is, we have calculated the solution of the PD by this expression, where this is the value of the alpha is 3 and L is 10. We will write u at 10. So the solution of this equation is u of xt is equal to summation n is equal to 1 up to infinity a n e power minus 3 n pi over L whole square t into sine L is 10, sorry, sine n pi over 10 to x. So this is the solution to the problem. We have to construct the first 5 terms of the solution, means we have to calculate a1, a2, a3. We will calculate the first 5 terms of the solution. So for the first 5 terms we must know a1 is equal to 2 divided by 10 integral from 0 to 10 f of x, which is x into 10 minus x sine 1 pi x over 10 dx. So I have calculated this integral using MATLAB. So this is equivalent to 25.8. Constant a2 is equal to 2 divided by 10 integral from 0 to 10 x into 10 minus x sine pi x over 10 dx. This integral is equivalent to 0. The value of a3 is 2 divided by 10, 0 to 10 x into 10 minus x sine 3 pi x over L dx. So the value of this integral is 0.95. Similarly a4 is 0 and a5 is 0.2. So using the values of these constant, we can write the solution u of xt. The first pipe term of the solution is u of xt is equal to 25.8 e power minus 3 pi over 10 whole square t sine pi x over 10 plus 0.95 e power minus 9 pi over 10 whole square t into sine 3 pi x over n plus 0.2 e power minus 15 divided by 10 pi whole square t sine pi x over n. So this is the first pipe term of the solution. Here C2 is 0, C3 is this one, C4 is also 0. Our next objective is to find the temperature at T is equal to 0. So at the midpoint of the rod, the value of x is 5 because the length of the rod is 10. So the midpoint lies at x is equal to 5. So we will substitute x is equal to 5 and T is equal to 0 to get the temperature at time T is equal to 0 at the mid of the rod. Okay. U at x equal to 5 and time t is equal to 0. I have calculated this thing as 25.05. We have simply to substitute x by 5 in this expression. Sine pi 5 divided by 10 sine 3 pi multiplied by 5 divided by 10 and t by 0. So we will get this result. The temperature at the mid of the rod at after 3 seconds is 1.7961. You can substitute t is equal to 3 in this expression and x is equal to 5 in this expression. Similarly, at time t is equal to 5 and x is equal to 5 means midpoint of the rod, and after 5 seconds means t is equal to 5. This is equal to 0.3039. Okay. Okay, this is enough for today, and inshallah in the next lecture we will continue our studies on wave equation. I hope a very good health to all of you. Stay blessed. Allah Hafiz.